Here, I'm in. Hi, there we go. Hello.
Okay.
So I'm in New Zealand. It's pretty late right now. It's 11:15 at night. So I try to keep it concise and short and interesting for you guys. Feel free to stop me if you have any question through the presentation. So, I understood that you were mostly interested in understanding, our modeling and what's behind of provisions and our plans of cleanup and how do we quantify plastic and how do we estimate plastic. So I tried to prepare something around those lines to basically going back all the way to 2012 when I really started to work on the subject. I started to play with dispersal models. So basically, they're like particles that we release in a computer, and we have a bunch of data on ocean circulation. So in that case, we use a model called ICOM, it's a global model, and we release particles from significant sources. So we try different scenarios, which are coastal scenario, river scenario, shipping scenarios, and then basically we release particles in the global ocean and we track them for a period of time. And we observe in the model basically the formation of garbage patches in subtropical waters. That's a paper we published in 2012, and that's basically the model we use. All the frameworks explained there. I mean, we had some improvements along the years with new data coming, especially for like source scenarios and so on. But this is basically the main model we're using. And in this model, we discuss in detail really like the formation of garbage patches and what they look like as you zoom in. And that's the figure I put on the bottom right, where we model, like we picture garbage patches as like accumulation zones, but really what they are like clouds of debris. And so as you zoom in, you basically see you have like gyres within gyres. So like basically concentration of plastic, of marine litter, and I guess other floating objects is very complex. And as you come into details, you start to observe that you have like small scale accumulation within larger scale accumulation, regional accumulation. So you'll note the figure I showed here on the top right is the formation concentration of particles, and that's what we call the garbage patches forming, and you see the yellow color. You'll note that I don't have any scales there because basically at that time we were just playing with just a numerical model, a number of particles. So that was just giving kind of a representation of the probability of where things can end up, but we didn't have any numbers to like basically back this up. And at that time, I started to get involved with other researchers in that field, and there's probably marine litter science I think is a really young field in general, and there's a lot of things that we're doing at the moment that we're just trying to invent the field in a sense. And here in this paper, basically, what we did is like we worked with a bunch of international researchers that actually went at sea and collected data using manta trolls, the surface of the ocean, and try to correlate basically what we find at sea with my model, and that I came up with that paper that Marcus Ericsson authored, and where we basically gave the first estimate of how much plastic we thought was coming, how much plastic was floating at the surface of the ocean. One aspect of that paper is that we started to differentiate plastic in size classes, and that's really important. We'll get back to it later. But like plastic pollution is a big word. It comes in many different types and size and shapes and polymer type, and therefore the fate of different type of plastic is different depending on where you are. Some of them sink, some of them float, and that's really important to keep that in mind. And we'll get back to that later. Another paper later on, we worked with other modelers. Basically, at that time, there were three main global models that were proposed. There was one from Nicola Maximenko and one from Eric Mancedil, and another one from me. And then basically, we did the exercise we've done with Marcus Ericsson only for microplastic data, and we tried to get the best estimates of surface accumulation from the three models. And then, more importantly, what we did is that we compared how well models were agreeing and how well they were disagreeing. And basically, we found that the models are pretty much agreeing like in large scale accumulation zone, and that's also where we have most data because most of this data has been collected over the years from a lot of time by just do-gooders and NGOs and so on, and people are interested to go and sample where plastic is, right? So we have a lot of data in garbage patches, but we don't have much data outside of it, and sometimes it's actually a bit problematic. But that was one of the main outcomes of the paper. And that leads me to 2015, where basically I started to get involved with the ocean cleanup, and Boyan got in touch with me, where we basically wanted to estimate in precision how much plastic and what type of plastic is floating at the surface of the garbage patch, the Great Plastic Garbage Patch. And that was, I mean, the idea behind this research really was to understand the problem and to give some sort of some information for the engineer and for the planners to see exactly what we had in, you know, what was the task for if you were to go and clean up the garbage patch. And so that research took several years. Actually, we started in 2015 with what we call the mega expedition, where we had a bunch of sailing boats that left from Hawaii and going to mostly California, and sampled at the same time in different places of the North Pacific Ocean. And that was really important for me to have this, because I wanted to have, you know, in one given time, like a lot of different samples over the ocean to basically have a better understanding of what was the outskirt of the garbage patch and what was the difference in accumulation at the surface. Because the previous work we had and the papers I was showing before, they were basically using, you know, 10, 15, 20 years of data stacked up together to represent the ocean. But the ocean is very dynamic, right? And so it was very important for us to have an image within a 1-2 months period, having as many samples as we could in a wide distribution, and have a, you know, better certainty in designing, or like in drawing the contours of the accumulation zone in the garbage patch. So it took the big expedition in 2015. We found a lot of ghost nets, like large fishing nets during the expedition, the mega expedition, but we just didn't have enough data to quantify the contribution of those objects into the overall pots. And so I remember back then, I said, like, well, what we need would be a sort of aerial survey. And we ended up a few months later basically jumping on that C-130 airplane that is on the bottom right, and we flew over the Great Pacific Garbage Patch, and we did 2 transects. They're like the light blue lines in the figure, to basically take, we took 7,000 auto photos that we, you know, made basically those slices and tried to like identify large nets. And so using those 2 field expeditions, with the model that we developed, we basically were able to give with more confidence the composition and the extent of the garbage patch. And so one of the main results, and that's the title of the paper, is that was the first time we actually proved that there was an accumulation in garbage patches, because until 2018, it was still not accepted that there was a significant accumulation of plastic at the surface of the ocean, even though, I mean, it sounds very trivial. In 1950, there was no plastic at the surface of the ocean, and now there's a lot of it. So obviously there's an accumulation. But if you look at the concentration over time for all the different samples taken for the whole North Pacific, you see that the overall trend is not increasing that much. And the problem we had there, and that's basically why I wanted to have this whole surface coverage in one given time frame, is that we were able to solve temporal variability, because that garbage, I mean, this area, this accumulation zone, you know, remains in the same region, but it does move over time, depending on what different cycles, basically. But that's something we saw in you can see in the graph, the second graph to the left. And so once we try to like follow the track, the patch, sorry, track the patch in time, that's kind of the outline that you see moving under long-term analysis. And then we took all the samples from like the early days, like in the 60s and 70s, and over time, and we took all the samples that were taken inside and outside what we think the accumulation zone was. We actually find that there is a clear increase inside the area and larger than outside the area, right? And that difference, having like a large accumulation inside and outside, really like shows us that, you know, the input is more than the output, and that there is a clear evidence that, you know, plastic is accumulating inside the Great Pacific Garbage Patch. But more importantly, like the result for us for the ocean cleanup really was to give this full quantification and classification of floating plastic in the North Pacific. And so those are like the main results. Basically, we come back to engineers. We said there was, you know, an average of 80,000 tons of floating plastic Very important, define the size class. We're talking plastic that is bigger than 0.5 millimeter in size. And all the subjects contain about like 1.1 to 3.6 trillion fragments that were basically scattered in an area of 1.6 million square kilometers. Really important, I think, in my opinion, and through this symposium you're having this week, is the two last points. Is, what we find when we show that's the figure B, there is like 92% of the mass that is carried by fragment that is bigger than 5 millimeters, and 94% of numbers of fragments are contained of fragments of less than 5 millimeters, right? And that's what basically the curve on the right bottom, the B curve is showing, right? You have the measured mass concentration, which is light blue, and you have the numerical concentration that is dark blue. And so what we're showing in our results is that basically, the finer the particles, and the x-axis is basically the size of the particles, right? So the finer your particles, the more of them, you have like millions of particles in the center of the patch, but they weigh very little mass. And then if you go to the large size classes, there's way less of them, but the mass is obviously increasing, right? And so, some of the questions we're asking at the moment in our research group is, if you stop the inputs, we don't have any plastic coming, how long for basically the material, like the transfer of mass to occur? Like for the large objects down the right, there's not many of them, but they carry most of the mass of the estimated total plastic floating. How long for this to basically drift towards the left, where the curve, the blue curve would go down on the right and up on the left, but then the large, the dark blue curve would go like, up to the roof, basically, as like large plastic is degrading on microplastics, right? So those are like the questions we're trying to understand, and what are the timescales for this to happen? For all this mix of macro fragments to occur once there is like large plastic that is already floating there. And so those are like the kind of things that we try to follow. But again, I stress like those two last points, that 92% of mass is carried by fragment larger than 5 millimeters, while you have 94% of the numbers of fragments that are carried by objects less than 5 millimeters. And I added actually into my presentation that little slide here after following some of the presentation from yesterday, because there's also like two models that were presented yesterday, and I think that the largest misunderstanding like in the community here today is contained here, right? Like, what is the promise of the ocean cleanup? The promise is to clean 50% of the GPGP in 5 years, and that's something that's been used in like the two models that were presented yesterday. Now, what's really important, right, is we're talking about 50% of the plastic mass, and that goes back to the previous result, right? Like 50% of the plastic mass, if we were only to target like the megaplastic, that is 0.0004% of the total number of objects, right? So it's really important that you understand what we're doing here. Like, we're not going, if you look at the left curve, there is like, basically plastic separated in different size class, blue, micro, to yellow, mega. We're not going for the blue stuff, right? Like, we're not pretending that we can, clean 1.8 trillion plastic particles, 50% of it in 5 years, right? And so, in that sense, like, it's really important to understand this, because the promise to clean 50% of plastic is the mass, right, in 5 years. And that does not require to span 50% of the GPGP surface area, like we, like I saw the presentation yesterday, and the Slack recharge, I was saying, well, okay, so I assume the velocity of the system is like 0.12 meters per second because we have to cover 50% of the garbage patch in 5 years. This is not what we're doing, right? Like, we actually, and that's something that Hendrik actually said yesterday, we want to operate in a very narrow area, which is the very center of the patch. And when we say the center of the patch, this is not just like there's a lot of plastic, we clean this, and then there's no more plastic. This is basically the area where you have the highest chance to receive plastic, because plastic is coming to you. And that was the whole definition of the passive cleanup system, as opposed to an active cleanup system, and having a system that goes like 50% of the garbage patch area in 5 years. That is an active system, right? We just want to be like right in the center where there's like the highest chance of plastic to come to you, right? And then the second point is the same. It's like, removing 50% of the plastic mass in 5 years, like, and that's what the graph shows on the left, doesn't mean we want to remove 50% of 1.8 trillion particles. And that applies for the sun as well. Because, I mean, to start with, it's unrealistic, even with like 60 system or 600 meters long. It's impossible to, like, even if like hope to get like 50% of those trillion particles, right? like the whole point where we want to go is really like to the yellow, to the gray, and the orange. Is like, if we manage to pick this up, like that's like more than 90% of the mass that has the potential to like turn into trillions of particles, right? If you just like leave it there. Well, this mass, right, represents a very, very tiny fraction of the number of objects that is floating out there. And so there was like the second model that I saw that was presented yesterday where there was basically a rate saying like, well, we've got 50% of removal of trash per 5 years. And so I think the number ended up being like 0.011% per square kilometers per month. And those rates were applied for floating life and, velas or Nostrum in general. This is wrong. Like, this is just not what we're doing, right? We are not going to like, try to scoop 50% of all the particles that are floating at the surface of the garbage patch, and we're not intending to, to rake or clean or try to cover 50% of the garbage patch. So I just leave that here. Maybe we can go back to that later on. I just want to finish on the science that we've been producing and explaining you what the models are behind, and then we can discuss that if you want. One point I just want to make also is like the science we've been producing with ocean cleanup has been such like a good opportunity to actually go out there in a place where people or like governments are not ready to invest money, right? No one really, no government's ready to like spend, like some money to go and study the garbage patches, right? And so we were able to go out there and that paper got like, so much publicity, and it just really showed that how the ocean plastic, story is like meaningful for people, right? And it's part of a movement, and it's, it's about cleaning up, but it's about like, stopping use of plastic. It's about intercepting plastic, rethinking our use of plastic. This paper has been, it's like out of like 2.8 million research outputs in 2018 was ranked 7 in the top 100 on metric, which basically measured the amount of tweets, newspaper article, blogs, and citations. It was also like number 1 for Nature Scientific reports, just showing like how this story is important and is bringing basically our problem back to us and say, hey, like we have a problem there. The study basically concluded with something that's is something like based on our research at the moment, is like trying to understand the missing plastic, right? There was basically, as we found a lot of plastic, 80,000 tons of plastic floating at the surface of the garbage patch. This is still like way less than what we think should be there. Like, if you assume like the number of the amount of plastic that's entering the ocean, right? And so that's what we call the mass balance budget. And that's one of the main stuff we have with the research team of the ocean cleanup is trying to understand what happens to plastic as it enters the ocean. There's estimates that gives in the order of millions of tons of plastic entering the ocean every year, and over the surface of the complete ocean, there's probably less than 1 million tons accumulated, right? So what's happening to all this plastic, right? So there's this discrepancy. There is mainly like 3 reasons that we can explain that discrepancy, I think. The first one is we overestimating the source. And that's not given because right now we have that study that talks about like 8 million tons of plastic entering the ocean. Now what we found over the last few years is that when we really like to try to understand like emissions of plastics from land into the ocean, I mean you need to understand like the physics behind it and the seasonality and the temporality and those kind of things. And that 8 million tons of plastic entering the ocean every year, there's no physics behind it. It's based on waste statistics, on population densities, and it was a great work to like bring like one step up. But I think we still don't really know like how much plastic is entering the ocean every year. So that's one point. The second point is like there may be an underestimation of the amount of plastic that is accumulated at the surface of the ocean. That's still something we're trying to work out. Like all plastic moves differently at the surface of the ocean, yet like the estimates we have use like one single solution that use only sea surface currents, but we don't like take into account like high wind edge debris and those kind of things. And we also know that plastic is distributed very chaotically. Like, I mean, it's very hard to say actually, even if you go inside the garbage patch, you'll be one day there's just no plastic, and another day there's like a lot of plastic, right? And models right now don't really take into account this noise. Like what we're trying to do is like we're trying to give some average over time and over space, but we don't really resolve really well that granularity of accumulation of plastic at the surface of the ocean. So we could also be underestimating that value. We don't know. And then, you know, the most simple explanation of what's been brought so far is like, well, plastic doesn't survive at the surface of the ocean and sinks at the bottom or is stranded on coastlines, right? And that's something that's been like commonly accepted by the general scientific community. And I'll talk about that paper that came out about 2 years ago now from my colleague Proponents that was basically talking about inputs and accumulation of plastic at the surface of the ocean and trying to link those two. And basically the paper was explaining that to have those two linked together, the only explanation is that plastic degrades very quickly. About, in the paper, it's about more than 90% of the mass of plastic floating at the surface of the ocean is assumed to degrade within 1 year and later settle on the seabed, right? And so the conclusion of the paper was like, well, if we kept the sources of plastic entering the ocean, then, with a very high degradation rate and settling rate, over 90% per year, then all the plastic that is at the surface of the ocean will disappear within 3 years. Therefore, there's no point of cleaning up the ocean, and, we should just focus on the source. End of the story, right? That's something. I mean, we'll discuss again after this, right? But the smog, basically what I call the degradation and the sinking of the seabed is something that we call the plastic smog, right? And that's something that we observed. Like we discussed this in previous paper in 2014, in 2015, and we discussed it in this other paper in 2018, where basically you see that the smallest fraction of microplastics. So on the right in the circle, you see the number and the mass is decreasing rapidly. More rapidly than it should if you were to assume that the larger microplastics would degrade into smaller microplastics. So there's this common understanding, or even apparent observation that shows that the smaller part of microplastic is missing from the surface of the ocean. So there's question whether this comes from sampling device or whether those microplastics are sinking at the seabed, right? And so there's the question then of size versus surface of microplastics, and so the smaller the plastic, the volume decreased by by the cube, and the surface decreased by the square, and so after a while, basically your surface to volume ratio becomes too small, and if you have any biofouling organism, the microparticles may be more likely to sink than larger objects that have a bigger rising velocity, right? So that's what we call the smog, and it's something that we actually went sampling for last year. We did a trip, you see on the bottom left, we went from Hawaii to California, and then we did 5 stations using a Loch Ness, that is the object that is on the right, and this is not at scale, obviously, and basically that allowed us to sample the water column at different levels from 2,000 meters down to the surface and try to give a profile of those missing microplastics. And as a result we got, we're defining those results at the moment, so it's not published. We show a degradation concentration and traces of small microplastics all the way down to 2,000 meters. So that is a confirmation of the smog. Now, if you look at the values, the order of magnitudes, we're talking 3 to 4 order of magnitude less at the bottom. So our understanding is that the smog and the degradation of smaller microplastic, and then the distribution of the smaller microplastics through the water column and then through the ocean is most likely something that happens, and I believe this. The time scale for this to happen and to be able to naturally, reduce the amount of plastic at the surface of the garbage patch, the flow to me is very small compared to the inputs, and even if you were to stop the input, I think for this material to degrade, we're talking just decades, and then to sink I don't know, to me it's much longer than what we saw. We wanted to measure this flux, and we actually deployed a sediment trap last year, right under the garbage patch. We went to pick it up 2 weeks ago. Unfortunately, the instrument failed and could not pick up the sediment trap. So I'm really glad about this, but that's the reality of oceanographic expeditions and experiments at sea. But in the meantime, we looked at other alternatives and tried to explain different stories of what's happening really with those garbage patch. And here there's a comparison of the plastic we find in the GPGP on the right, and on the left is the plastic we may find more next to sources and next to coastal environment. And if you see, the plastic is completely different, right? On the left you can still identify it. There's a lot of wrappers. And on the right, you actually don't see any wrappers, you don't see any plastic bags, you don't see any plastic straws, like all those sort of plastics that are like very present in the discussion. Actually, is not really concerning the garbage patches. What we find in garbage patches is really thick, floating HDPE, polypropylene, those kind of plastics that just like degrade very slowly, like those bottle caps. I'll make a quick, so that was one of the conclusion basically, like only certain type of plastics have the capacity to persist at the sea surface for extended period of time and accumulate in oceanic plastic pollution hotspots. That was one of the main conclusions of our 2018 paper. And I'll just talk about that story that came up like a few months ago. That was a publication from my colleague Anela Choi in Scientific Reports that was reporting levels of microplastics in the Monterey Bay in deep sea. And like journalists jumped on that and were like, well, it turns out there's actually more microplastic in the deep sea than the Great Pacific Garbage Patch. The Great Pacific Garbage Patch is nothing. And I mean, that's how like journalist terms. What happens is that really, like you need to talk about, you need to be sure and make sure what be serious about what you're talking about, basically, because here, like the plastic that Anela's reporting, she's talking about PET, PA, and PC, like all those plastics, right? They are not floating. So there's not the plastic we're studying. We are finding in the Great Pacific Garbage Patch polypropylene, HDP, LDP, and so like those are like really not found actually in the study, unless maybe I think it's PSA, but even anyway. So that's it's just not comparable. So it's very important when we talk about plastic pollution to define your polymer type, and then again I'm going to put that one here, the size class, right? Because again, we say, oh, there's more microplastics, but actually, Anela like sampled on the size class that is actually way smaller than we sampled in the Great Pacific Garbage Patch. And so, yeah, I mean, like the plastic pollution science is something that the smaller you look, the more you find, right, in terms of like number of particles. So, like you have to be careful in the conclusion you make, and make sure that the study are comparable and you're talking about the same type of plastic. There is no one plastic, right? There's different type of polymers and they have different fates. And also when you try to be quantitative, it's really important to make sure that you're talking about the same size class and the same sampling device, because otherwise it's just not comparable. What we've been doing over the last few years, like collecting plastic in the Great Pacific Garbage Patch, is to basically what I call plastic archaeology. We've been, documenting full organism labels and brands and languages and production date, and try to collect as many clues as we can on the plastic we find to try to tell the story of where is this plastic coming from and how long has it been there and how long will it be there, right? And so those are like typically the things we find and we document, little brands and people. That writing here talks about the Philippines. So that gives us some information. Maybe it was made in the Philippines, maybe it was used in the Philippines, but even though it's not sure, right? And then another thing we look for is the pollution date on plastic, right? That's how pollution date looks like. That basically on the left tells you the year, that's 96, and the arrow gives you the month, so that's May 96. So this plastic was made in May 96, and it was found in 2015, floating at the surface of the ocean. We've done that for all the different large debris microplastics that we found, and systematically looked for clues and collected production dates, and that allowed us to give a sort of estimates of like population age in the Great Pacific Garbage Patch. And so the oldest recognized object is actually a crate from the 1970s, but there could be older objects, but we just didn't find any pollution dates. The older pollution that we found was the 1970s, and that's the population size we have from observations from the debris. And actually, you have very, very little small or like young objects, because well, maybe they haven't reached the waste stream yet, and then they probably haven't reached the ocean, and then they probably haven't traveled to the Great Pacific Garbage Patch. Even though we found one within 5 years of age, most of them were coming from 5 and 15 years, 15, 25 years, and so on to like 50 years old. Now, we're like, can we actually try to model this and try to estimate the population, the age of the population of plastic in the Great Pacific Garbage Patch? And so to do so, we first look at the inputs and say, okay, we use that paper from Laurent that came in 2015 or 2016, I think, that basically talks about the different use of plastic in our society and when plastic is entering end of life So basically you have packaging where everything comes using the first year or so on, and then you have industrial machinery or building and construction where the end of lifetime for plastic products is more like 20 years for industrial machinery or 35 years for building and construction. So we took those into account, and then we look at the share of polymer by demand by market sectors, so like all those market sectors. We look at the evolution of plastic demand from the 50s to now, and then we only consider floating plastics, like we discarded PET or plastic bottles, we discarded PVC, those kind of things. And so once we have this, then we have every year we have an estimate of what is the proportion of the different type of plastic reaching their end of lifetime per market sectors, and we can fit it into a simple box model that we built for the ocean. So our model, basically, we have emissions coming into the coastal environment, and then plastic floats at the surface. We're talking about floating plastic, macroplastic, right? So everything larger than 5 millimeters. And so that plastic, basically, once it's entering the coastal environment, can either strand on the shoreline or be transported offshore or stay in the coastal environment. In the meantime, all the plastic, whether it's stranded in the coastal environment or in the offshore environment, can degrade in smaller microparticles with a degradation rate that is kept constant per type of plastic. And then the plastic that is stranded can also eventually be released into the coastal environment, and basically we do so years after years from the 50s to present, and we try to keep track of what is the age of the population. So like we have basically bar charts of like different age of all the total of plastic that is in all our compartments, right? And so what we try to do is like, well, let's try to reproduce observations that we see offshore, and we vary all the different parameters from 0 to 100%. Basically, we're talking about mass of plastic, and we found that the main parameter that is basically, acting on the age pyramid, the population of plastic is the degradation rate, right? Because the other ones, the population in the coastal environment will be representative later of the offshore environment, right? And so actually the transfer between stranding and transport offshore doesn't matter really. Like what matters is the degradation rate, right? And so what we've done is that we varied the degradation rate from 0 to 100%, and we made those 4 graphs so that the model age distribution. And the bar chart, the whiskers on the bar, they show all the value possible by varying all the other parameters of the model from 0 to 100%. So that shows you like how basically the degradation rate really like how you remove objects from the system is really impacting the age of the population of plastic, right? And so to get the best fit with our observation at sea, we found that actually we had to have a degradation rate that was rather small. We found a best fit that was about 3%, and that's in good agreement with some studies that have been conducted on the field where they leave like plastic for long period of time in the ocean and look at how far they degrade. And so the amount of mass that is removed and transformed into microplastics for those objects per year is in the order of 1 to 2 to sometimes 3%, but actually below 3%, right? And so that was just a good confirmation. Now, the thing is, if we have a small degradation rate, then how can we explain that there is not that much plastic at the surface of the ocean, right? Well, in our understanding or in our model, we explain it by the factor that the coastlines is filtering the plastic into the ocean, right? So we use again like particle models, and we release particles from different source points along the coastline. That's based on statistics of waste and population densities. And so what we find is that within a year, there's 97% of all the particles that we released that have spent at least like 2 days, consecutive 2 days next to the coastline, right? And so basically increasing the chance of bleaching, right? And so our understanding is that plastic, once it's released in the ocean, actually is really good at going back onto shore, and debris gets stranded on the coastline. And there's only one tiny little fraction that really makes its way offshore, but that plastic that goes offshore, is highly persistent. It's a very small fraction. We talk about 0.1% of total plastic that we think we waste into the ocean or discard into the ocean, but that really tiny small fraction is highly persistent and managed to make its way all the way to the offshore ocean, right? And that's what we are doing really in this study. there is like confirmation for like those kind of observations. I mean, one thing that doesn't come into those budgets, those mass budget analysis, is actually the cleanup impact. Like humans do clean up, coastline. Municipalities do clean up their coastline, and so there is a removal from cleanups from coastline back into the waste stream, right? And those things are not taken into account yet. But if you go to remote islands where there's no one living, you see there is like drastic accumulation over the last 10, 20 years of basically plastic accumulating on shorelines when it's not being looked at, right? And that's a direct confirmation of basically what we're trying to say here is that plastic to move to like garbage patches have a very low chance to like reach it, and there's many things that may remove it to make it go all the way there. But once it's there, it's highly persistent, and the water actually like absorb UVs and slows degradation, and that's well known by like material scientists, right? So trying to explain the discrepancy between source and estimates of amount of plastic floating at the surface of the ocean, and explaining this by saying, well, plastic degrades very quickly in the ocean, and basically that the seabed to me was just not good enough, right? And that's how I got into this whole story and saying like, well, it's not as easy as that, right? Like that plastic floating out there to me is probably there if it's remained untouched. It's probably there for like decades, if not centuries. That changes the implication. That's basically what I was trying to say, right? So if we use a model basically, and then again like we produce research on marine microscience, but it's also in the frame of the ocean as a support for like planning, operations, and strategy and so on. We look at the future of where are we going from now, right? Like if you look at production forecast for plastic and so on, like I mean we're hitting the fan, right? And that's kind of like the curve we show, and on the left you have microplastics, on the right microplastics floating at the surface of the ocean, and we look at the impact of okay, let's just focus on source reduction, right? And so we put pretty ambitious goal of 80% source interception reduction by 2025 and going to 90% by 2040. And so what we see there, that's the blue curve, the light blue curve, we see that the microplastics basically plateau, actually decreases very slowly because, like plastic is, like the 20% left interception is basically compensated by the degradation over time of older objects, right? But if you stop sources and leave all that trash floating out there, you have basically your fragments, the amount of fragments, microplastic fragments that keep on increasing, right? And that's I mean, to me it's trivial, but yeah, you kind of have to produce science and papers to like show that, right? But that's kind of what we're showing. And then the other option is like, well, let's just focus on cleanup, and then I mean the same answer is like, well, you can clean up plastic in the ocean, but then if you keep pouring plastic in the ocean, you just cleaning up for like ever, and actually like with population increasing and plastic use increasing, like even 12% annual cleanup, that is the ambition of the ocean cleanup. It's just not enough, and we make it done for 10 years, when after 10 years things like continue to increase, right? And so that goes down to that solution we've been supporting for a little while. Say, well, if you really want to like be serious about like trying to clean the ocean, you obviously need to reduce plastic at the source, and you need to clean up the legacy, right? So when we talk about cleanup, I'm talking like about old plastic, and when we talk about interception and even upstream mitigation, we're talking about the new plastic over the next 10, 20, 30 years. What are we going to do about this? And so I think it becomes, like it's pretty clear now that solving that issue is going to come in multi different options and strategies, from upstream, from governments and from industries and from citizens, but also into like trying to intercept plastic and clean up plastic, because there's always be some accidents and some floods and some spills here and there, and yeah, that's kind of like something that we're trying to like show here. That we need like combination of different strategies to like try to like get out of that mess. An interesting result that we have here is that even if we again like we're talking about like extremely ambitious scenario, 12% annual mass cleanup and 80% source mass interception. We've reduced the amount of like microplastic at the surface of the ocean, but the microplastic, the small stuff only plateaus, right? Because again, I think even though we show that we managed to pick up some debris, some microplastics there, I don't think it's feasible or like it's an idea to like say that we'll be able to clean all the microplastic in the ocean, right? But the large stuff we can go at it, right? And that's I think the point we're trying to make here. So going forward, at the moment we're participating into this group, the FLOTSAM group. That's basically a group of like several oceanographers that study marine litter, and we're trying to do a whole review of basically all the different physical system or physical mechanism that drives the transport of marine litter at sea, and how does that vary with plastic type, and like we're fully aware as part of the community that those things are really hard to predict and to model, and it's probably the same with marine organism and nostrum and so on. But yeah, that's basically something we're working on, and now we want to be like better at predicting plastic in the garbage patch, in the accumulation. We just had a field expedition the last few weeks where we conducted quite a lot of, we went to go get our sediment trap, and in the meantime we used our operational dispersal model and used also satellite imagery to look at sea level anomalies and try to correlate or find if there is some sort of correlation between cyclonic and non-cyclonic eddies and surface accumulation of plastic inside the garbage patch. This is work in progress. Obviously, having the ocean cleanup operating in that region is a great chance for us researchers to learn more about the dynamics of marine debris, but then I guess also like the dynamic and the life of nostrum and marine organism. I just found that find we had actually on the last expedition, like you see in the red circle, that's our current. This is full of Velella. That's actually the highest area where we put Velella. We were like collecting plastic. We found most of our plastic on the left on the map, basically inside the garbage patch. But the largest station we have with Velella is this one. I mean, the other ones probably had maybe one or two sometimes, but this one was just full of it. Interestingly, that was outside the accumulation zone of plastic. I mean, I know Velella, and they have like different types, right? The northwest and the southeast or something, and they have their little cells. So, it's same as plastic. I mean, there's plastic that moves only with current, some other moves with wind. How is Velella moving? I don't know, like I never like modeled that, but I think, yeah, those are like questions basically I think are really relevant to that workshop here you're having. And I was, I talked to Rebecca, and I imagine she's in the room. Over the next few years, we want to do more. We want to do more sampling, and I mean, I'm primarily interested in plastic, but definitely happy to accommodate more sampling for nostalgic life and plankton and other like free floating organisms, and trying to see also how they are affected by plastic and how impacted they may be by populations. Thank you very much for listening, and I'm happy to answer your questions now.
Do you have a moderator, or should we just call out? Should we use a microphone?
We have a microphone here.
Okay, I'm gonna get a microphone.
Yeah.
Hi, how are you? This is Rebecca.
Hi.
Can you hear me? Okay, so I want to make sure I have some numbers correctly as we move forward with our modeling here. So you say that according to your findings, 3% of plastic that enters the ocean at some point will remain in the ocean as opposed to being beached on land. That 97% of the plastic that enters will eventually be beached on land. Is that correct? I want to confirm.
Yes, within a year, that's correct.
Okay, so within a year. Okay, so and then you say, well, others have said about 30% of the total plastic that persists in the ocean is in the Great Pacific Garbage Patch. Do you agree with that?
30% of?
Plastic that's persisting in the ocean. So of that 3% that does not beach within a year, 30% of that is in the garbage patch. Is that right with your models?
That would be all right. I'd say for all the surface accumulation, maybe, yeah.
Okay, and then you're saying 3% of the garbage patch plastic by mass is small plastic. Is that correct?
Yes, I say 8% of the microplastic is the mass. Yeah,
8%.
Of the mass is made of microplastic.
8%, not 3%. Okay, so if I have those numbers correctly, 3%, 30%, and 8%, that means that 0.072% of the plastic is the plastic that you're concerned about that persists. 0.072%. Is that correct?
Yeah.
Okay.
I mean, probably, yeah.
Okay, no, I just want to clarify one more thing really quickly. So you're saying you're collecting 50% of the plastic by mass in the first 5 years? Is that correct? But that's mostly large nets? So what? So why does it matter that 0.072% of the plastic in the patch may persist?
Well, I mean, okay, first, when you say 3% of the plastic makes it stay offshore, that's on a yearly basis, right? Obviously, plastic, is being, mixed and goes back offshore and inshore and offshore and inshore, right? On a yearly basis, we're saying there's a really small fraction that really makes its way, and the rest, most of the degradation anyway, I think, happens on the shoreline, right? So it's not only 3% and 97% is on the shore and it's outside of the model, right? It's still contained in the model, right? That's the first thing. The second thing, all the plastic that is, say, buried in sediments, and I think 99% of the plastic that we put in the ocean so far is likely near coastal environment in the sediment buried and probably lifted every now and then by large storms or by operational dredging, or is just making its way down on the seabed through gravity, right? That plastic, it's buried in sediment. I think we should leave it there. It's a shame, generations later they will find it, but it's,
even though it's probably impacting marine life in the sediment?
Well, I don't know. I mean, I think to me, if you tell me, okay, to me, floating plastic has much more impact than plastic buried in sediment.
Why?
But, I think that, why? Because, all the transports of invasive species, provoke ingestions, entanglements.
So you don't think sedimentary animals ingest plastic?
Yeah, no, they probably do. They probably do, for sure. But I think, generally speaking, I think there's a much wider range of organism and life that is impacted by floating plastic than only, organism living in sediments. But
So so you think that more organisms will be impacted by floating plastic than plastic on the seafloor? I just want to clarify that.
I don't know, but to me that sounds kind of floating plastic to me sounds much more seems to have much more impact than plastic buried in sediment that may actually not move. But yeah, for sure it has some impact.
Is that plastic buried in sediment or plastic on the seafloor and below the seafloor?
That is plastic on the seafloor getting buried by sediment.
So both on the seafloor and below the seafloor?
I'm not saying plastic in the sediment is great, but I'm saying that...
No, but we're trying to model this, so I just want to clarify that...
I'd rather have a large net buried into sand, on some lagoon somewhere than floating and getting strained on some reef and corals and getting spills and
Sure, but
the idea I have in my mind.
To clarify, so just to clarify, so plastic on the seafloor, in sediment on the seafloor, you're saying that those are sort of the same. So if there was a net on the seafloor, that's also included in what you're saying?
Yeah.
Okay, so you're saying don't clean up plastic on the seafloor, clean it up at the surface.
I'm not saying don't clean up.
No, but you were saying we should probably leave it there. It's a shame, but we should leave it there.
Well, I don't know, if there's a way to, go and dig into plastic and I don't know, I did some studies on seabed mining, and like here off the coast of New Zealand, they're trying to get iron ore on the seabed, and read some papers, and everyone saying like, don't touch the sand. There's a whole ecosystem there. You just don't want to like touch it, right? So that's one point. I don't know. I mean, that's not something we've been looking at really. Like we've been focusing on something like plastics.
So you're saying don't touch the plastic on the seabed because there's ecosystems there.
If it were heavy metals, we would certainly say that. Because heavy metals get remobilized.
Yeah.
For instance,
Yeah.
if you take out a dam.
Oh, sorry, he can't hear you, so maybe you should.
Well, I'm sort of. I'm just suggesting that if it were heavy metals, we would certainly say that you should not try to dig into it and remobilize those bad effects. So, and that happens with lots of things.
Sure.
You shouldn't destroy the ecosystem to save the.
So you shouldn't destroy the ecosystem to save the ecosystem, is what he's saying. That's what Scott just said.
I don't know, like, yeah, okay, all right.
Okay, so I think I have all of my numbers correct. So thank you.
Sorry.
Because the point you're making is about the newstone, so let's talk about the floating plastic, right?
I just wanted to correct one thing, because you mentioned 30% ends up in the Great Pacific Garbage Patch. That's not a number that we have researched or studied or confirmed. So validating that is a bit, I don't want to have that. Megan.
Oh, well, I just want to clarify one thing really quickly. So that was actually from a study that was published by another group. So that is a published number. I don't know if you didn't publish it, but that is a known number.
Hi, I have two questions. First of all, you were speaking both in the talk and with Rebecca about the plastic affecting the marine life. Can you point to specific publications that discuss the effect of the plastic on the marine life in and near the garbage patch?
Yes, I can, definitely. There is like some studies on the amount of plastic like ingested by fish in the Great Pacific Garbage Patch that was published by NOAA, and I think that was 2010 or so, around that time. Yeah, so there's that, and then there's the different like literature on invasive species, and yeah, things like we find it basically coming from Japan and arriving in Hawaii. Yeah, and then there's a paper that came out like a few weeks ago that's saying that they found like accumulation in microplastics on the south of Big Island. I don't have the name of the author, but like I can find that to you. I mean, obviously there's tons of literature out there, and not only the Great Pacific Garbage Patch, just like open ocean. Right?
I mean, you're specifically wanting to clean up the garbage patch, and that's why I'm interested in the effect of the plastic in the marine life. I've read the fish study, but have not found loads of literature that you're referring to. So I would love if you had further resources.
The one I'm talking about, right? That's the one that came out like a month ago, like the south of Big Island, right? And they look at like juvenile fish and the amount of like juvenile fish versus microplastics. I mean, Hawaii is in the Great Pacific Garbage Patch. You just have to go and travel there, and you'll see that it's just not fair. They're like getting waves and waves of those debris, and those debris are getting like smaller and smaller, and it's exactly what that paper is discussing, right? I mean, so what is the question? Like, are we saying like basically there's no literature saying that there is impact of plastic on marine life in the open ocean? Like,
that the literature is limited on it, and that seems to be sort of the nexus of the project, is that you're cleaning up plastic because there's a negative impact. I'm simply asking for evidence that there is a negative impact. My follow-up question is, I know that you focus just on the plastic. Can you give any suggested estimate of, if you do deploy some mechanism in the middle of the garbage patch, as you suggested, to clean up the large pieces of plastic, what percent of newston would be collected?
I may not be the best person to ask this. Hendrik would be better at answering this. But
well, you said earlier that my estimate was completely wrong, and so I'm asking you to suggest a different estimate.
Yeah. Okay. Sorry. Megan.
Yes.
Sorry, I didn't say your estimate is completely wrong. What I'm saying is that, if you take, the whole surface of the ocean, there's like, or the North Pacific, right? There's 1.8 trillion plastic particles. You say like, okay, so the ocean cannot consume 50% in 5 years, therefore, 50% of the population and 50% of the plastic particles going to be removed in 5 years. This is not what we're saying. And I know that, you say that, every models are wrong and so, but, like the framework can be easy, but the main assumptions got to be right at the beginning, right? And so what I'm saying here, do you guys have my screen visible?
Yeah. Yes. Yeah.
That goes back to here, basically, right? If we're looking at, like, we're not going to the blue, like, we're not going to pick up, like 1.8 trillion pieces of plastic particles and try to rate all the surface of the ocean, right? We're talking 66 times at, 600 meters long, that's 36 kilometers total length, right? That's, I made the math, that's 2% of the total Hawaiian coastline, right? And so what I'm saying is the rate that you use, saying, well, it's 50% in 5 years, and therefore it's the same for medusas or organism, and so it's 50% in 5 years, and so that means like it's 0.02% per square kilometers per month. That's not what we're doing. Like, we're not going to scoop all the surface of the ocean in 5 years and try to get 50% of the plastic stuff. We're trying to stay in a very narrow area where we have the maximum chance for plastic to reach us. And if you catch one ghost net, that's one ghost net is billions of microplastics, in terms of like plastic mass of material, right? And that's what we're saying, right? So that goes back to that number here. If you look at, you're talking 0.02% per square kilometers per month. I'm saying that 0.00004%, right? So that's a factor of like 500 or something. That's for the total number of objects, right? And that's that's the same comment I had for like Richard to say, well, there's like 1.2 million square kilometers. If you want to cover like 50% of that, you have to travel that speed. It's like, it's just so there's a basic misunderstanding of what we're trying to do here, right? And I don't have a value like you're asking me of the amount of percentage we will remove, with one system. And that's something we're trying to study now with the bycatch data and so on. What I'm saying is like it's way less than 0.02% per square kilometers per month. Like that assumption to me is essentially wrong. And I'm not saying it's completely wrong, but I just wanted to raise this, right? And this whole discussion and this whole symposium, I think, goes back to that misunderstanding. It's like, 50% of the garbage patch means that we're going to scoop 50% in 5 years of the surface of the ocean. This is not what we're saying we're doing.
Okay.
So can you provide us with the model then? Because we're using the model that you have published, right, on the website. So that's the challenge, is that this is what it says on the website. You're saying that that is not correct?
Are you using?
So you're saying 50% of plastic will be removed from the garbage patch in 5 years. So we're modeling based on what you said on the website. So that's what if Laurent is saying it's more specific than that, can you provide us with that so we can use it? Because otherwise we just have what you say on the website.
Yeah, no, I understand. So what I say, okay, is like we're trying to clean up 50% of the plastic mass, and with our results, even if we thought, at that graph you look at 90% of the plastic mass, that's like the three top categories, right? That's like 10% of the top in terms of like numbers, right? So that means there, like we don't need to scoop 90% of the surface of the ocean to remove in time 90% of the plastic mass, right? Now, what I can provide you is a dispersal model. I mean, I'm happy, like the dispersal model is open source. We can work with you. We can give you trajectories. You need to look at it, and that's why we do dispersal model, right? That's why we try to stay in the high concentration zone, and we don't go at the plastic, but the plastic comes to us, right? That's a plastic system, and that's the concept behind. So, I mean, I can provide you with trajectories. I know Andrew plays in the room, like play with the trajectory of plastic and also like some removal systems that basically we're reproducing the systems, and the removal of this plastic, we can apply that to Nuston, and look at it as well. But what I'm saying is like by just looking at that graph here, like in the promise, is like, if we remove 50% of the plastic mass of those large objects and we expect them to like, at some point travel to us, we only like targeting a small tiny area of the full North Pacific Ocean. We don't want to go around like all the ocean. We leave the ocean, the rest of the ocean as it is. And yes, we will have some impact on some organisms because we're scooping stuff out of the ocean, and we do that. But my point is that, yeah, like what I understand is like you're not like collecting or scooping all the surface of the ocean to get to 50% of the mass. So
Right. So
the definition of the model is published. The input model is open source. The HICOM is publicly available.
right. So I think if you're able to help us by providing us with the ocean and river models as open source that you use, then we can actually use those. So the ocean models that you're using, yes, but it would be really helpful to have like your code, your that, so we can then just use that directly, because otherwise we have to recreate it. We don't know, right? So if you could provide your ocean and river models and code, is that possible? Can you do that?
Well, so there's two different things, like ocean, rivers, models, and codes. Like, so, like what we're doing is, we're using an ocean model that is not ours, so that's publicly available as HICOM. The river model is an estimate of points, and so we can give you an estimate that is publicly available. The definition of the model is publicly available. I can give you my MATLAB script.
Yeah.
You can run models.
So basically, whatever models you've been using to calculate, your numbers for ocean and rivers, right, to estimate 50% of plastic in 5 years, I mean, that's what we need.
Yeah, that was published about 8 years ago, and I mean, I can give you my script if you want, and you can.
Yes.
Hendrik can give you this, I guess, because he's there and he's working with this model. Definitely. I think that would be the best way, and that's how I saw it anyway. That's what I told you over the phone before. I say, you need to build a dispersal model, and then, I mean, the difference between plastic and any sort of life is that, life is like making babies, right? So, like, you need to take that into account. We don't do that, even though all plastic degrades, so they make like microplastic babies. But, you need to go dispersal, and if you don't have any dispersal model and necessarily France, then you can use a plastic model for sure.
Great. Thank you.
I'll be happy to give you this. Yeah.
Are there other questions? Okay. Other questions? Laurent, thanks for your talk. It's Roger Cook used to say that his worst critics were his best friends. It's clear that you have lots of friends in the room here today. Congratulations. Thanks.